Generally, we've treated electricity and magnetism as two different chapters in our textbooks. We have moving charges creating magnetic fields and stationary charges creating electric fields. This is Purcell's classic explanation of magnetic forces. Picture a wire carrying a current. Positive charges flow to the right, spaced by an average distance, L. For the wire to stay neutral overall, negative charges sit still, spaced by that very same L. So there's no electrostatic force at all on a test charge, Q, sitting outside the wire. But what happens if that test charge also moves to the right, at the same speed as the flowing charges? Let's switch into the test charge's own rest or lab frame and see what changes. Here's the wire, drawn in the lab frame. Positive charges stream along the wire to the right, while an equal number of negative charges sit fixed in place, keeping the wire electrically neutral overall. Both rows share the same average spacing, L, and the positive charges drift along at speed v. A distance r away, we place a test charge, Q. Let's have it move to the right too, at that same speed v as the current. Positive charges moving, negative charges at rest. Net result, the wire is electrically neutral. Therefore, there's no electrostatic force on a test charge Q outside the wire. Now let's watch this exact same scene from the test charge's own rest frame. Here's that same wire, copied over into the test charge's frame. And since it's the negative charges doing the moving here, the velocity arrow now points to the left. The positive charges are now at rest. Because wire has same velocity. Because they're moving, they spread back out. The average distance between them is length contracted by the Lorentz factor. That gives us two different spacings, L plus for the positive charges and the contracted L minus for the negative ones. Meanwhile, the test charge itself is at rest in its frame, and it now feels a genuine electric field, E, pointing toward the wire. Because the negative charges are packed more tightly, the wire looks negatively charged overall. And that net negative charge is exactly what pulls the test charge toward the wire, back in the lab frame. We call this force a magnetic force. Quantitatively, the separation distances in the test charge frame work out to this. L minus equals L times the square root of 1 minus V over C squared. And L plus equals L divided by that same square root. Let's tuck this figure into the corner and work out the numbers. First, let's find the linear charge density of the wire in this frame, assuming V is much smaller than C. It's Q over L plus minus Q over L minus, which, written out using our two spacings, becomes Q over L times the square root term minus its reciprocal. Expanding both square roots to first order in V over C, the leading terms cancel, and we're left with lambda equals minus Q over L times V over C squared. So the electrostatic force on the test charge, still working in this frame, is Q times E, which comes out to Q V squared, over 2 pi epsilon naught, R, L, C squared. Remember, R is just the distance of the test charge from the wire. Now boost back to the lab frame. This exact same force shows up there too, with the same magnitude, as long as V is much smaller than C. Let's write it in terms of the current, I equals QV over L. That gives us this expression for the magnetic force. The expression sitting in those parentheses has to be the magnetic field strength, B. And notice, the quantity, 1 over epsilon naught C squared, is exactly what we usually call mu naught. So magnetism isn't some separate force of nature. It's just electrostatics, combined with relativity.